Overview of the market opportunity. Satellites are now essential for commercial, military, and scientific purposes, demanding robust memory solutions for reliability and efficiency in harsh space environments. With the satellite services market set to reach $357 billion by 2025, component manufacturers are integrating into the satellite supply chain, facing challenges like cost management and competition. Major low Earth orbit satellite suppliers are focusing on integration, technological innovation, and partnerships, while also dealing with challenges such as capability, cost management, supply chain resilience, and fierce competition in a rapidly changing market. While supporting SpaceX's active involvement in space exploration, the U.S. government is also reviewing relevant organizational structures, including a potential adjustment to the role of the National Space Council in order to streamline the decision-making process. Meanwhile, aiming to reduce its reliance on U.S. satellite systems, the European Union is developing an independent military intelligence satellite system. Through the IRIS program, the EU plans to deploy 290 satellites to ensure secure connectivity and digital sovereignty. Additionally, by 2025, the EU aims to complete the integration of member states' military satellite systems under the GovSatcom program to enhance regional coordination. Rapid market demand growth of low Earth orbit satellites. Recently, the need for low Earth orbit satellites has been skyrocketing, way ahead of what medium Earth orbit and geostationary Earth orbit satellites can offer. This is because low Earth orbit satellites are just better when it comes to technology, cost, and communication uses. Technology drivers behind the low Earth orbit satellite boom. 1. Low orbit, low latency. Low Earth orbit satellites offer lower latency and better signal quality than traditional geostationary satellites, making them perfect for real-time applications and connecting remote areas without infrastructure. With the rise of 6G, which demands higher bandwidth and lower latency, memory solutions need to be faster and more efficient to handle massive data. 6G satellite connectivity relies on decentralized data storage, boosting security, privacy, and reliability. This setup will change global data management, especially in remote areas where traditional networks are missing. 2. Cheaper launch, smarter tech. Thanks to reusable rockets, like SpaceX's technology, satellite launch costs have dropped significantly. More satellite companies are also adopting automotive-grade memory, which keeps costs low while still meeting performance needs. 3. Small satellites, big coverage. Low Earth orbit satellites are smaller, cheaper to build, and easy to deploy, offering global coverage, especially in remote areas. This opens up significant business opportunities. 4. Short lifespan, fast innovation. With low Earth orbit satellites having a lifespan of just 4 to 6 years, there's a constant need for replacements, driving innovation and growth in the satellite industry. 5. From radiation hardness to radiation tolerance, the new space standard. Unlike deep space or geostationary satellites, low Earth orbit satellites often rely on radiation-tolerant, industrial-grade, or even automotive-grade components instead of fully radiation-hardened parts. While not as robust as radiation-hardened designs, these components offer a significantly higher reliability than standard commercial-grade parts, especially in harsh environments like space. This approach reduces cost and development time, but increases the importance of system-level resilience. As a result, strong error correction, data redundancy, and fault-tolerant architectures are now essential to ensure mission success. This shift is reshaping satellite design philosophy and redefining how the aerospace industry balances performance, reliability, and cost. Radiation source and satellite space environment. Currently, satellites in low Earth orbit are positioned relatively close to Earth, flying at altitudes between 160 and 2,000 kilometers, with most staying below 800 kilometers. Why do we pay special attention to these satellites? Because they are primarily used for missions such as communication and Earth observation. In these satellites, semiconductor memory is a critical electronic component in the payload computer's data storage system. These systems need to store large amounts of data, such as communication logs or telemetry data, especially when transmitting high-resolution images or videos. For low Earth orbit satellites to operate normally in space, they need to rely on various electronic components to be able to withstand the impact of ionizing radiation in the radiation environment. The sources of ionizing radiation in space include protons and electrons confined within the Van Allen radiation belts, which are divided into the inner belt and the outer belt. The second is high-energy subatomic particles caused by solar flares, including protons and heavy ions, as well as cosmic rays formed by supernova explosions outside the solar system, which are also mainly composed of protons and heavy ions. The radiation encountered by low Earth orbit satellites primarily comes from the inner Van Allen radiation belt, which the satellites pass through multiple times each day. This belt is located approximately 1,000 kilometers to 12,000 kilometers above the Earth's surface. And in the South Atlantic anomaly, its boundary can drop as low as about 200 kilometers above the Earth's surface. The inner Van Allen radiation belt consists of high-density electrons with energy in the range of several hundred keV, as well as protons with energies exceeding 100 MeVs. While operating, the electronic components inside low Earth orbit satellites are primarily exposed to radiation from protons, with the proton radiation flux typically ranging from 10 quantifor per square centimeter to 10 toin per square centimeter per day, depending on the energy levels. The impact of space radiation on electronics. For electronic components mainly based on semiconductors, the damage caused by space radiation can be broadly divided into total ionizing dose and single event effects. Introduction to total ionizing dose. In the high radiation environment of space, electronic components gradually accumulate damage, with the most common being total ionizing dose. What is total ionizing dose? Total ionizing dose refers to chronic degradation caused by prolonged exposure to radiation. It can lead to charge trapping in the chip's insulating layers, voltage shifts, increased gate leakage current in transistors, degradation in performance, parameter stability, or even total functional failure. Why perform total ionizing dose testing? Total ionizing dose testing simulates radiation accumulation over the duration of a space mission, helping ensure that components continue to operate reliably throughout a satellite's lifespan of 5 to 10 years. The total ionizing dose is typically not expected to exceed 1 crad over the entire mission. However, customers often require testing at higher levels, sometimes even up to 20 crad. Relationship between single event effects testing and total ionizing dose. During single event effects testing, it's essential to track the total accumulated dose, as it can influence how the device responds under single event effects conditions. If the component is particularly sensitive to total dose, it is recommended to conduct total ionizing dose testing first, followed by single event effects testing, to avoid misinterpretation of results or the need to replace the sample. Introduction to single event effect. Single event effect refers to the phenomenon where high-energy particles, such as cosmic rays or solar particles, pass through semiconductor materials and deposit charge within the device, causing immediate electrical disturbances or damage. This effect is instantaneous and unpredictable, and is especially common in high-radiation environments like space, posing a significant threat to the stability of electronic equipment. Common types of CE, single event upset, is also known as soft error, the change of state of a latched logic cell from 1 to 0 or 0 to 1. A single event upset is non-destructive, and the logic element can be rewritten or reset. Multiple cell upset, the change of state of 2 or more logic cells induced by a single ion strike. The corrupted cells are usually, but not always, physically adjacent. Multiple bit upset, a particular case of multiple cell upset when the corrupted cells are in the same word. Note that multiple bit upset cannot be corrected by a single bit error correction code. Single event transient, a temporary voltage excursion, such as voltage spike, at a node in a logic or linear integrated circuit, caused by a single energetic particle strike. This type of disturbance is temporary, but it may lead to misjudgment or the transmission of incorrect signals. Single event functional interrupt, a soft error that causes the component to reset, lock up, or otherwise malfunction. Single event functional interrupt typically occurs in complex devices with built-in state control sections like in memories. Two main types of single event functional interrupt are distinguished depending on the actions required to restore operability, reset by software or by power cycling. The stored data may or may not be lost. Single event latch-up, a permanent and potentially destructive state of the device under test, whereby a parasitic thyristor structure is triggered by an ion strike and a low impedance, high current path is created. Single event burnout, triggering of the parasitic bipolar structure in a power transistor, accompanied by regenerative feedback, avalanche, and high current condition. Single event burnout is potentially destructive unless suitably protected. As the electronic components continue to shrink, the oxide layer becomes thinner, and the effects of total ionizing dose gradually diminish. However, the effects of single event effects become more severe. This is because the component's capacitance and operating voltage shrink, and the transient current caused by heavy ions or protons exceeds the component's operational current. Additionally, a single heavy ion or proton strike can affect a larger number of components as the size of the device decreases. Therefore, compared to total ionizing dose, single event effects are of greater concern when exploring radiation effects. To effectively test both single event effects and total ionizing dose, using protons as the radiation source is an appropriate choice. Unlike deep space or geostationary missions, low Earth orbit satellites don't require radiation-hardened components. Instead, they often use radiation-tolerant industrial or automotive grades. While this approach makes satellite design more cost-effective, it also increases the risk of errors like data corruption or loss. That's why it's critical for components like NAND flash memory to have strong error correction capabilities. These features ensure data integrity and keep systems running smoothly, even when exposed to space radiation. Now, we've seen that radiation-tolerant solutions provide an effective and cost-efficient design approach for the low Earth orbit environment. For a deeper dive into radiation-tolerant products and solutions, please stay tuned for Part 2.